So, it would be nice if rocks came labeled out in nature, but they don't. And so we will be, especially when we're going out and about, we're going to be looking at different kinds of rock formations. We're going to be trying to figure out what they are based on the minerals we see in the rocks and the organization, the structure of those rocks. And so it's important to be able to know what kind of properties to look at in order to identify some of these minerals. Now, I've given you a hard copy of this as well, so you can take notes as I'm going through. There are really a handful of properties that we'll be looking at in the course. Color, as we'll talk about in a minute, is really only diagnostic for a few different kinds of minerals. I think what you will find most useful will be things like cleavage, hardness, streak, luster, those, and to some extent density, although that's kind of a hard one to measure in the field other than just kind of a general, this rock feels heavier based on its size than some of the other rocks. So color, we have some situations where color is diagnostic. What mineral are we talking about here in the yellow? Sulfur. Okay. And pretty much any of the different kinds of morphologies of sulfur that you'll come across will have some kind of yellowish appearance to them. They aren't the only things that are yellow, but it's a good clue. Here we have olivine, and generally speaking, you'll generally see a green kind of tinge when you come across olivine. A greenish color in rocks is not all that common, and so if you do see it, it's a good idea that it might be olivine or maybe apatite or serpentine. Here, however, we've already talked about this combination already. What's this mineral?
Magnetite, hematite.
You're half right. It's hematite and hematite. Okay, so these are both hematite. Clearly, you can't say that hematite is rusty red or silvery black because it can be either. The difference here is basically just what's going on in terms of the surface composition of the mineral. Yeah, I first came across hematite in a big way when we took a trip to Kenya one year, and there were all sorts of hematite jewelry. So it was all this metallic forming hematite, polished nice and bright. And I would not look at this. After that, I would have no idea that coming across this sample that wouldn't have triggered the idea of hematite in my mind at all. So, and this is a case where color is quite misleading. Color can be variable though, but still be useful. So here are different species of quartz on the top, and different species of calcite on the bottom. And I mean, the quartz are all basically the same kind of three-dimensional silicate mineral. It has the same kind of properties in terms of no cleavage, it fractures, and so forth. What do you suppose is resulting in the difference in the coloration among these different species of quartz? Impurities. One way to say it would be impurities, but the different kinds of trace elements, trace cations that are built into the matrix will determine whether you have this kind of clear-ish quartz, more comparable to what you think of as quartz, or this milky quartz. The milky quartz also, I think, has some issues with small air spaces that have been incorporated into the quartz matrix, and that scatters the light in such a way that it gives it that milky appearance. But certainly this amethyst quartz and the rose quartz are colored the way they are because of the trace amounts of different cations, metal cations that are incorporated into the quartz. Same thing with the calcite. So while the color is not diagnostic of quartz, the fact that this quartz is purplish lets you know that it's amethyst quartz, and it's going to have certain certain ratios of magnesium and iron and aluminum that are incorporated into the quartz, distinct from the ratios that are in the rose quartz. Here's just another example of the quartz. So the colorless quartz is almost pure silicon dioxide. The rose quartz has some titanium in it, and the amethyst has a significant amount of iron. Okay. Now streak is, as we talked about, a little bit more diagnostic, and we have streak plates up here. The streak plates are just unglazed ceramic squares. They're a little rough enough to grind off small particles of the mineral as you rub the mineral hard against the porcelain surface. Okay. And so you can see from this figure from the display at the American Museum of Natural History, if you take a look at these different minerals, sulfur, no surprise, gives a yellow streak. But, for example, this rhodocorsite, which looks kind of pinkish, actually gives a white streak when you streak it on the ceramic disc. Here are the two forms of hematite again. So this one looks gray and shiny. This one looks dull and rusty red. But when you streak both of them onto the plate, you break down those differences in surface structure, and they both show up as these kind of rusty red streaks on the ceramic plate. Now, you do not need to cover the ceramic plate with all of this streak in order to do a streak test. Just means you have more crap to clean up off of the plate later. I don't even know why they did that. Okay. So hardness is an interesting diagnostic. It's easy to do. It's something you can do easily in the field. What geologist is not out in the field without a penny and a fingernail and a zinc nail and a pocket knife and so forth? So the hardness scale is actually defined in terms of some indicator minerals, starting with talc down here at the bottom as the softest mineral, gives a score of 1. And diamond up here is given a score of 10. And basically, any combination of minerals in this sequence, the one with the higher number will scratch the one with the lower number. So if you take a piece of quartz and rub it against a piece of talc, the quartz is not going to be affected. The talc's going to have a big gouge in it. There are a couple of minerals over in the tins over there that look fairly similar, but you can easily distinguish in the field because with your fingernail or your thumbnail you can scratch the one and you can't scratch the other. So look for that. So here's just an example. Again, calcite and quartz. The calcite is when you scratch them together, pieces of the calcite are being ground off and deposited on the quartz. Which one is the harder mineral? The quartz. Okay. So quartz is hardness index of 7. Calcite is hardness index of 3. Now this is not a linear scale. You can actually, with instrumentation in the lab, quantify a measure of hardness. And in particular, these values at the high end are really not not linearly related to the index values lower. So, fluorite is maybe approximately twice as hard as gypsum, but just because one is 4 and one is 2 doesn't mean that that's the case. Diamond is clearly about 3 times as hard as the corundum, but it's only difference between 9 and 10 on this hardness scale. Hardness scale was actually developed early in the history, before some of these more quantitative tests were designed. So again, this relates back to the crystal structure and the kind of matrix, crystalline matrix that the minerals have. The covalent bonds provide the strongest mineral structures, mineral crystalline matrices. And diamond, of course, is nothing but carbon-carbon covalent bonds throughout the whole piece, which is why it's at the top of the scale. Ionic bonds, which would be where you've got the cations and the anions kind of electrostatically associating with each other, would be weaker. And then the van der Waals or hydrogen bonding would be the weakest of all. So we've got graphite over there, we've got talc over there. The talc in particular is at the bottom of the scale because it has just a whole lot of platy sheets in the material that are held together by weak van der Waals hydrogen kind of bonding between the layers. Crystal habit, you would think, would be a useful trait, but as we've talked about, most of the times you don't have crystals have enough time and space to actually exhibit their full form. But this reflects how crystals will grow when they are precipitating out of solution or when they are crystallizing out of a melt. It's the ideal shape, but regularly it's not actually realized in real minerals. There are these very distinct shapes of crystals that we can talk about defining. You will see these affecting the overall shape of some of the minerals you'll be looking at today. So we have salt crystals over there. We have halite in one of the bins, and they're not going to form a perfect, six-sided dice shape in real nature, but you will tend to see faces at right angles to each other in kind of equal scale, as opposed to other crystals that might also be at right angles but more stretched out. Some of the minerals over there clearly display some of these slanted orientations, and you can kind of pick those out as you're looking at the crystals, at the minerals. Cleavage is a little bit more useful. No matter how the mineral grows in its environment, if it breaks, you can ask the question, does it break along a smooth plane or does it fracture? And so something like, if you take a look at the quartz, there are no smooth planes across which the quartz has split, but something like the muscovite or the biotite micas have a clear cleavage plane that you can see. The feldspars have nice clear cleavage space planes that you'll see on the minerals. And depending on whether there are 2 preferred planes or 3 or 4, whether those preferred planes of cleavage are at right angles to each other or are at some kind of not right angle, you can identify different minerals. So 3 cleavage planes at right angles to each other is the situation for the halite, the sodium chloride crystals. And you can see, I mean, they don't look exactly like dice, right? But if you look at them, there's overall kind of a picture of, well, I see a plane here and a plane here and a plane here, and they're all kind of at mutual right angles to each other. Here's just another, I mean, here you can see some of the biotite and muscovite that's over there. You see clearly has one pronounced and very a cleavage plane that allows it to be cleaved off in very large, flat plates like that. Again, this reflects the difference in strength between the different bonds and how those differences in strength are oriented in the crystalline matrix. In something like quartz, where there is no weak direction, it's not going to cleave in a flat plane. It will break, but it will have to, you'll have to kind of irregularly split open the covalent bonds, and that splitting is not going to follow some smooth plane throughout the mineral. When you do see either crystal habit from crystals being able to grow in an unencumbered situation, or if you're looking at these cleavage planes for situations where there are multiple cleavage planes at a particular angle, those angles will always be the same because it's defined by the relationship among the atoms in the unit cells, the basic fundamental component of the mineral. And we have some tools that we can measure angles on some of these cleavage planes. If looking at the hand samples, you think that that's something that's of use. Again, cleavage when there's a plane of weakness, fracture when it's not. Fracturing very common in the quartz. Here's an example of chert mineral. Also flint and obsidian. Those are all minerals that don't have a particular cleavage plane, and they've all were very important in Stone Age technology, stone cutting tools, because you could flake off bits of the stone, the mineral surface, and leave very sharp edges to them. Okay. Luster. Things are either going to be metallic or non-metallic, basically. But even if they're non-metallic, they can have Luster is basically how does the sample reflect light. And so we have, I think I've got some galena over there, which is a metallic ore. And if you look at it, there are clear, bright, shiny, mirror-like surfaces that clearly reflect, and you would say that that's got a metallic luster. Many of the other minerals are non-metallic, they're going to be more earthy, but some of them still have either a waxy or a silky kind of sheen to them. That can be a diagnostic character, so you want to be able to look at a mineral and note what kind of luster it has. And then specific gravity. To do this right, you'd actually have to measure the volume and the weight, and then you could calculate the density. But the more mafic minerals, the minerals that are more have higher proportions of some of those heavier metallic cations in them, are going to have a higher specific gravity. And in particular, many of the metal oxides and metal sulfides you're going to be able to tell them because they're going to feel like they have more heft to them than some of these other minerals. And then finally, there are some other things. As I said, we've got some hydrochloric acid up here. There's one class of minerals in particular that we talked about in lecture today that is likely to react with the hydrochloric acid and give off bubbles. Which class? Carbonates. Okay. So again, some of the carbonates are less reactive than others, but many of them, if you put a weak acid solution on them, that is going to break down the carbonate anion that's in the mineral structure. It's going to result in carbon dioxide gas being released, and that gas is going to accumulate in the little drop of acid you put onto the mineral, and it's going to show up as this bubbling. Other minerals, some minerals are metallic. This is actually an example of an iron meteorite, but what common mineral, which is an iron oxide, would be magnetic? You mentioned it earlier. Magnetite, okay. And we actually do have some magnetite, but I don't think I put it out because I think 24 samples is plenty enough for us to look at. So I thought I would structure this lab just very simply. I've got a fairly generic data sheet. You've got 24 lines here. Rather than having a column for each of these properties, I've kind of grouped them. So there's a column where you can just note what you see that's of interest in terms of cleavage or fracture or crystal habit, whatever you can see that's related to those kind of related aspects of the mineral for a given sample that you're looking at. Color and streak, luster and transparency, translucency is somewhat related to luster. They're oftentimes talked about similarly. So there are some of the minerals over there that are somewhere between transparent and translucent. There are others that... What is the difference between transparent and translucent? If something is transparent,
you can see directly through it.
You can see through it. See through it easily. That does not mean colorless. Colorless and transparent are two different things. An old style glass 7-Up bottle would be transparent, but it would not be colorless. What color are the old 7-Up bottles? Green. Okay. The difference between transparent and translucent.
Clear.
What?
Is it clear? Is that the difference?
Well, transparent is sort of, clear is somewhat a common term synonym for transparent. Translucent is not clear, obviously, otherwise it would be transparent. But for example, well, I'll let you look through and see if any of these you think are translucent. Translucent, the light can penetrate to some depth and be scattered, but doesn't go completely through the mineral. Now, to some extent, that's a function of how thick your piece of mineral is. You take any mineral and cut a thin enough section, and polish it. The mineral is going to become translucent to some degree, or even transparent. But you can take a look at some of those. It's clear that the light is doing more than just bouncing off the surface. So, it looks like the light is getting at least a little bit into the mineral before being bounced around and back. So we can spend basically all the time we have, or until your minds fall out, looking at different minerals and recording what you can see in terms of these properties.